Okay, hello everybody. So let's try to finish our chapter on random vectors today. And next time, which is Friday morning, we're going to start discussing conditioning, one of the most important concepts in probability theory. But before that, let's finish our discussion on independence today, okay? And we will also look at some family of random vectors, Gaussian vectors, okay? So last time we talked about the definition of independence of sigma algebras. So independence of sigma algebras and independence of random variables. So remember that we defined independence of sigma algebras first, and this is basically a product type of rule about random variables that are measurable with respect to those sigma algebras. So if we have f1 to fn, so independence of f1 to fn means what? So you pick random variables, z1 measurable with respect to this one, zn measurable with respect to this one, and the product of the expectation of the product is equal to the product of the expectations. And then we talked about some further characterizations. Then we defined independence of random variables, let's say x1 to xn, as the independence of their corresponding generated sigma algebras. So this was for a general case where this x1 to xn can take values in some abstract measurable spaces. Today I'd like to state a corollary, or let's say also a proposition. There are some parts that one needs to prove, but I'm going to state it without proof because the ideas in the proof are similar to the ones that we used before. So let's say we have, so let x1 to xn be real valued random variables. And you can also state a version for just numerical ones, allowing plus and minus infinity. So real valued random variables on some probability space, omega fp, then the following are equivalent. So the first one is that x1 to xn are independent. The second one is that you can write down the cumulative distribution function of the vector as the product of the individual cumulative distribution functions. So for all x1 to xn, and let me also say where f is the CDF of the vector x, and fi is the CDF of xi for each I. So we already had some general theorem about the independence of random variables, and we had 4, 5, 6 conditions there. I don't want to repeat them. I'm just adding new properties that are only valid for real valued ones, because we can talk about cumulative distribution function when we have real valued ones. Okay? But the other properties, like you take functions of x1, fn, xn. So we had such a property in the previous theorem. So this is still true. This is still valid, but I'm not writing it because we're in the special case of that theorem. So this is still there, okay? I'm just adding some new properties in the case of, in the real valued case, okay? So we have also the product rule for the Fourier transform, or the characteristic function. So this is R1 x1, Rn xn for all vectors R. So suppose xi's are positive, okay, for all I. In this case, we can also have the Laplace transforms. So if you can multiply the Laplace transforms of the components to get the Laplace transform of the vector, this means they are independent. And finally, suppose x is continuous with density G and xi has density Gi, then we have G of x1 to xn, the joint probability density function, is the product of the marginal probability density functions. But I should say for Lebesgue, almost every x in Rn. Because, you know, there is the problem with versions, right? Versions of probability density functions. In other words, if you have some probability density function and you just change its values on a null set with respect to the Lebesgue measure, namely if you change the values of it on rationals, then it is still a version of the probability density function. So I cannot just say there is one joint probability density function and it is the product of the unique probability density functions of the components, but I should rather say if I have, G1, Gn, it's typo. So if I have G1, which is a version of the probability density function of the first component, and Gn, which is a version of the probability density function of the last component, then their product is a version of the probability density function of the vector. This is the more precise way of saying it. But yeah, the way we find one version of the joint PDF is just to multiply the marginal PDFs. And this is good enough. I mean, versions, all versions have the same type of properties in terms of calculations. So I will just leave the proof. I will just omit the proof. OK? Proof omitted. And the arguments are about, for instance, if you want to look at the cumulative distribution function, this is about pi systems, right? So those rectangles like minus infinity to x1, minus infinity to xn, they form pi systems on the product space and also on the individual real lines. And these values characterize the joint distribution. So if you have this property, you can conclude that the joint distribution of the vector is the product of the marginal distributions, right? This is the meaning of, one meaning of independence, right, from last time. So this is the distribution of x, and this is the distribution of x1, and this is the distribution of xn. And so number 3 and number 4 are extensions, multivariate extensions of the theorems, which say that Laplace transform determines the distribution, Fourier transform determines the distribution. That needs a proof, but we don't care too much. And finally, you can maybe pass from cumulative distribution functions to density functions. by differentiation and so on. So just to finish this discussion on independence, I'd like to also talk about the simplest type of independence that we learn in elementary courses. So what is independence of two events, right? If you have two events, their independence means the product, the probability of the intersection is the product of the individuals, right? If you look at three events, this is the product of the individual probabilities. Am I right? So is it the definition of independence of A1, A2, A3? Anybody who took a course, undergraduate course on probability? Was it the definition of independence for three events? Something's missing here. You need to also check the two-way interactions, right? So this is not enough by itself. And we have 1, 3, and 2, 3. So this is for two events. This is for three events. So we're going to define the independence of n events. So A1 to AN are called independent if their indicators are independent as random variables. Okay, so we define independence of sigma algebras. Then we define independence of random variables. Now we define independence of events by using the independence of random variables. Well, you could have also defined this using the sigma algebras generated by A1, which is like full set, empty set, A1 and A1 complement. But anyway, so the characterization of this is that so A1 are independent if and only if we have the following. So we don't look at just the intersection of everything, but we need to pick indices A1 to AI1 to AIK, and this should be the product of the individual probabilities for every k between 2 and n. Let's assume n is greater than 2 here, okay? Otherwise, it becomes meaningless. For every 2 to n, and I1 to IK distinct indices in 1 to n. So you pick, if you have 4 events, you look at pairwise intersections, three-way intersections, and then there is the intersection of everything, right? And this is going to be a homework problem. It's a quite boring proposition to prove. So I just don't want to spend time here. And this finishes the discussion on independence. But now I'd like to discuss with you how to use it in actual computations, okay? So we're going to look at one example. Let's say we have x, which is gamma, with parameters a and 1, and y, that is gamma, with b and 1. So a, b are positive numbers here, shape indices. And the scale parameter which is like the lambda of an exponential, is just 1. Okay? So, and we also assume x and y are independent. By the way, this is the independence symbol. If I did not mention this yet, this is the meaning of it. Okay? So this is what is given to us. And now we define a random vector out of those. U, which is the sum, and V, which is the fraction of x in this mixture. Okay? So let's say x and y are two random quantities, maybe of some chemical material or something like that. So you mix them, and this is the ratio of x in the mixture. And this is the total amount of material that you have. So what is the joint distribution? So the distribution of UV. What is the distribution of UV? This is the question. In other words, we are given the distributions of x and y. And since they are independent, we also know the joint distribution of x and y, just the product of the individual distributions. And now we look at the sum and this ratio. So UV form a random vector, right? What is the distribution of that? So what is U in du and V in dV? This is the question. So let's first recall what we mean by gamma. So x in dx is, so this is what we know. So this starts like an exponential distribution, right? Just x, x to power a minus 1, and then gamma function at a, dx, and x is positive. Similarly for y, dy, and since they are independent, their joint distribution is just the product of the individual distributions. So how can we determine the distribution of UV, the vector UV? So you want to write it as x over u or something like that? Okay, then what should we do? Okay, so can you come up with a general method, general idea? Did you solve the first question of this homework 6? Okay, what did you use? What method did you use? Okay, so you followed the route of cumulative distribution functions, okay? You can, of course, do it here. You can try to calculate the probability u is less than u, v is less than v, okay? But there is also a more transparent method which doesn't need any differentiation or anything, okay? So after you get your cumulative distribution function, you need to differentiate and so on to get the densities. And usually we want the densities like here. So this general method, we discussed this at some point for the real valued case, just one random variable case. Now we're going to use it for this vector uv. So let's say nu is a probability measure on, let's say, this, because they're all positive, and this is even between 0 and 1, right? It's because it's a fraction with the Borel sigma algebra. Okay? So just remember that UV has distribution nu if and only if its expected value is given as FD nu for all positive measurable or bounded measurable or bounded continuous F. And this integral is in fact a double integral on this space anyway. We're going to follow this method, which is very nice. Okay? So let F be from this R plus and 0, 1 to reals be a bounded continuous function so that it is Riemann integrable, etc. Okay? So it is just a generic function. We don't assume anything about this function, okay? Just regular enough to evaluate integrals. So let's try to calculate this expected value of f of uv. So uv is a vector, and when you apply f to it, you get a scalar, you get a real number, right? So this becomes a real valued random variable. We cannot evaluate this because we don't know the distribution of uv. But we know what u and v are. We can see it as x plus y and x over x plus y. So I can now see it as g of x and y, where gxy is f of x plus y, x over x plus y. Right? Why did I do that? Because now I know the distribution of xy. I know the distribution of xy, it's here. So we can evaluate this, right? We can evaluate this. So gxy times the distribution of this vector. Well, this is on this space. So it's a double integral. So let me write it in full. So x plus y, x over x plus y. Now e to negative x, x to a minus 1, gamma a dx. This is from 0 to infinity. Well, I made a mistake. This is now about x and y. They are both positive. They are both positive. Okay? This is for x. This is for y. They are both positive. Okay? So then the distribution of y dy 0 to infinity. And the hope is to get, let me write it in parentheses. So the hope is to make some change of variables, etc. here, and get something like this, f uv du dv. Because if I can make this u and this v, whatever here is going to be the distribution of uv. Okay, so let's play with the inner integral first, okay? So we have a fixed y, and we let x plus y equals u. So this means dx equals du, right? Just usual calculus way substitutions. So let's continue this computation. Okay. So I have my outer integral, which is still there. And now the inner integral is what? So dx becomes du. X becomes u minus y. So this is f u, and what is my x? Well, x is u minus y and x plus y is u. And now comes the limits of the integral. So x starts from 0, so u starts from y. Y is fixed here, goes to infinity. I just made this substitution in this integral. So now I'm stuck because I have y to infinity here. And we're done with our tricks about this inner integral. So what should we do next? Swap by which theorem? Fubini, or maybe we should say Tonelli here because we picked bounded continuous. Let's say Tonelli. So now, y is between, u is between y and infinity, right? Something like this. So now this integral for du is going to be from 0 to infinity. And the integral for dy is going to be from 0 to u. 0 to u. And everything else stays here. Well, everything depends on y here, right? Let me write this. E to negative u minus y, e to negative y. This becomes an e to negative u, right? E to negative u. Let me write it here. And I made this mistake because that was supposed to be a. Over there, you see my typo, right? So this was supposed to be a minus 1. So let me write them. U minus y, a minus 1, y, b minus 1, right? They all depend on y. Well, that's it for this integral. And I also have some constants. Let's keep them here. Did I forget anything? So these two became e to negative u, so I have a du. That's the only thing I forgot. Okay, now what? Now what? Look at my end result that I want to get. I want a v here. Now I have this here. So I need to kill this. How can I kill this? How can I make this v? Well, you see, u minus y over u is just 1 minus y over u. Let's call it v. I do it for fixed u. We are in the inner integral. I do it for fixed u so that this becomes y. And what is dy? Well, it is just u dv. Just u dv. So let's continue here, okay? Okay, so now f of uv and u minus y is just u times v, right? U minus y is u times v. So u times v, a minus 1. And y is just 1 minus v times u, b minus 1. Okay, so this is done, this is done. There is gamma a, gamma b. Well, what is dy? Minus u dv. Minus u dv. And let's also be careful about the upper and lower limits. So my u is fixed. The lower value for y is 0. So when y is 0, v is 1. When y is u, this is 0. So this is 1 to 0, and I have a minus. So let me just rewrite that as plus 0 to 1, okay? So this is 0 to infinity, 0 to 1, f u v, okay? So this is my dv integral. So I need something here, okay? And this is my du integral. I need something here. So, well, what are the terms about u? There is u to a minus 1, u to b minus 1, and there is u. So this makes a u a plus b minus 1. And there is e to negative u here. Right? This u term, and this one. They are all here. Okay? So what does it look like? This looks like what? This looks like a gamma distribution. This looks like a gamma distribution. All I need is my gamma function in the denominator. So if I divide it by gamma of a plus b minus 1, no, just a plus b, this is going to be a gamma distribution. This is going to be the probability density function of a gamma distribution. Of course, I just made it up to make a gamma distribution, so I also multiply this integral by this gamma a plus b. And I had gamma a, gamma b here. And I forgot to put my v and u terms, so there is, v term. So v a minus 1, 1 minus v, b minus 1, right? So we are done. We are done because exactly we got a form with an f u v, and everything else is going to be the joint distribution of u and v. So here's what we get. So u in du, v in dv is, let me first write the u1. Where u is positive and v is between 0 and 1. What do you observe there? So what does it look like? So can you say anything about the marginal distributions of u and v from this result? How can you get the marginal distribution of u here? This is the joint probability density function of u and v. How do you get the marginal density of u? With respect to v. So if you do it, what are you going to get? This term is going to disappear when you integrate it from 0 to 1. So integrate with respect to v over 0, 1, we get u in du, which is the gamma distribution with shape index a plus b and scale parameter 1. So u is gamma a plus b. Similarly, if you integrate with respect to u, you get the distribution of v. And this is called the beta distribution. Okay? This has a name, v a minus 1, 1 minus v b minus 1, dv, where v is between 0 and 1. So we say V is beta A, B. Okay. And finally, since the joint distribution is the product of those two distributions, U and V are also independent. And that is extremely surprising because you have x plus y and x over x plus y. So if you have just, let's say, sine of x times y and cosine x times y, you would say for sure they are not independent because you have x appearing in both random variables and y appearing in both random variables. So this is kind of a special case that you have a function of x and y, another function of x and y, and they happen to be independent. So the only actual trick here is to make up this gamma a plus b, but the intuition for this is that you want to have a gamma distribution here. So in order to have a probability density function, something that integrates to 1 from 0 to infinity, you really need that constant. Otherwise, this would be a finite measure, right? You want to have a distribution, so you want to have this correction term, like here. Okay? So all you do is to see those terms about u and recognize it as try to recognize it as a gamma distribution. So you come up with this gamma a plus b. And you also have it here, because you don't want it at the end of the day. And this becomes another probability density function called the PDF of the beta distribution. So V is, so this beta distribution takes values between 0 and 1. It is the distribution of this fraction, x over x plus y. And so if I just asked you this distribution of u, the question is, of course, much easier. It's not a joint distribution. It is just the distribution of x plus y. So you can prove in a much easier way that x plus y is gamma with a plus b and 1. That has a much easier proof. But since you have a random vector out of another random vector, you need to work harder to get the distribution of this new vector. Okay? So I think if you're going to learn one concrete method in this course, this is a good one, okay? So if you're going to forget everything about probability, the theory, measure theory, et cetera, just learn this, and at least you can calculate some stuff in a nice way, okay? So you can still do some practical applications, okay? And there is no differentiation. It is just substitutions and whatever. You don't need to go through cumulative distribution functions. Indeed, if you take f to be, the, let's say, 0 to u bar of u and 0 to v bar of v, this would give you the joint cumulative distribution function, right? If you specialize into f equals, so this is less than some threshold, this is less than some other threshold, this would be, this would give you the cumulative distribution function. So the calculations about the cumulative distribution function, joint cumulative distribution function, are not really different. Yes?
Would be there any problem if I choose a specific f at the beginning and compute everything with that?
Of course, there would be a problem because we have the theorem which says for all f.
Yeah, I
okay?
know, but for maybe calculations, there's an easier method for just a specific f if I find one.
So the issue is that if you know the distribution of u plus v, it doesn't mean that you know the distribution of u and v. So you either need to work with all possible functions f, bounded continuous, bounded measurable, positive measurable, blah, 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 or you can work with special functions like Laplace transforms, Fourier transforms, cumulative distribution functions. So the class of functions that you pick here should be rich enough to characterize the joint distributions. Okay? So CDFs, it's fine. Laplace transforms, it's fine. Fourier transforms, it's fine. General Fs, it's also fine.
Probably this is the most easy one.
Well, it depends. It depends. Sometimes Laplace transforms are easier. Okay? And in the new homework, there is a question about that. In fact, I asked you to prove that x plus y is gamma, but I have no v, so you just need to use x and y and try to calculate the Laplace transform of u using the Laplace transforms of x and y. Okay? That is almost like a one-line calculation. Okay. In fact, so there is another method which I'd like to discuss with you. So the nice thing about this calculation is that you can do the substitutions one by one. Sometimes it is not that easy. Sometimes, so you have x and y, and you apply a transformation, let's call it R, which gives you x plus y, which is u, and x over x plus y. So while xy lives in this space, r plus cross r plus, u and v live in this space, right? U is here, v is between 0 and 1. And the transformation is really one-to-one. In other words, it's also invertible. What is the inverse transformation? Well, if you know u and v, you can also go back to x and y. And so if you multiply u and v, you get x. And if you multiply u and 1 minus v, because 1 minus v is y over x plus y, so you're going to get y. So this is the inverse transformation. So there is a method. It is more of a calculus method than a probability method, which does this change of variables in one shot using Jacobian matrices. Okay? Jacobians. Okay? So what is the Jacobian of this transformation? Well, it is a matrix, so it's going to have the derivative of R inverse. I should write u and v here. So it is the derivative of this function with respect to u, the first component. So this is the first component, right? Derivative of the first one with respect to the second variable. Derivative of the second component with respect to the first variable. And derivative of the second one with respect to the second variable. You form a matrix. And what is this matrix? Let's calculate it. So this is V. This is U. This is 1 minus V. And this is minus U. So if you calculate the determinant of this matrix and take the absolute value, you get negative uv minus u1 minus v I guess you get just u in absolute value. So it's the absolute value of the determinant, not just determinant. Determinant is minus u. OK, so let me state, or let's look at this as follows, OK? So f of uv, OK? This is what we look for. And this is, OK, expected value of f of x plus y, x over x plus y. So what is this? So f x plus y, x over x plus y, times some joint distribution. Well, let me write blah, blah, blah du, blah, 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 dx, blah, blah, blah dy. So what you want here is to make a transformation and get f of u and v. Times what? Times what? We want, of course, du and dv. Maybe I should write some joint. So the PDF of xy, OK? Let me write it in a general way. So how are we going to figure out what is to be written here? OK? So the answer is by this Jacobian stuff. So, OK, I need my g of x. What is x? X is just u times v. U times v. I need my y. This is u1 minus v. And I also need my Jacobian, the absolute value of the determinant of the Jacobi matrix, which is u. This is, if you remember multivariate calculus, this is like how you pass from Cartesian coordinates to polar coordinates. You have dx, dy, but you have r, dr, d theta. Okay? That r was the Jacobian. Okay? And now this is your new, this is the probability density function of the vector uv, which is, of course, you don't need to do all those substitutions, because what is g? Well, g is just this, right? This times this. So if you write it down, e to negative uv, uv to a minus 1, gamma of a, d times e to negative u1 minus v, u1 minus v to power b minus 1, gamma of b, and times u. And if you, so it is this, right? Exactly this. So if you continue doing this simplifications and making them like probability density functions, you will get the same result. So it is just the simplifications of those steps for substitutions. So it is really all about calculus. So I tend to forget such things. I don't really remember how to calculate Jacobians, etc. So I personally always prefer to go with substitutions whenever I can. Of course, if I cannot, I have to use this method. If I cannot do it one by one, if it gets impossible or too complicated, then there is a shortcut. OK.